Section 5. We have two more sections left in this chapter. We talked about one-to-one functions or one-sided limits existing. We talked about limits in general. Now we put them all together to discuss continuity. As it's known, any function f of x whose graph can be sketched over its entire domain, unbroken motion in one motion, you never pick up your pen, is called continuous. That's an example of continuity in the function. But that works great if you have a graph of it. How do we know if it's continuous? By not having a graph of it. So by looking at the function itself. For example, if we had this graph. There you go. You still finished? Write that down.
Oh, I can.
No, go ahead. While you're there.
Okay.
And summarize what you can. Don't write word for word. Use abbreviations. So here's the graph. What do you notice about this graph? What can you tell me about any of these parts? We have three questions. At which number does the function appear to not be continuous? Why? And what about the other numbers? So what do you notice about this graph itself? Okay, you say you can call it piecewise, right? What else?
It jumps
Where?
at 1 and at 4.
At 4, why not at 2?
Oh, yeah.
No, we only have one jump discontinuity. What is a jump discontinuity? When it's approaching two different values. So on the only jump discontinuity you have here is at 1. Because on the left-hand side, it's going down to 0. On the right-hand side, it's going to 1. That's a jump discontinuity. What are 2 and 4? What are those called? Very good. Those are what we call the removable discontinuities. Why are they removable discontinuities? Right. And have we seen that before? Yeah, in the first couple of days of class, where we had x squared minus 1 over x plus 1. It's not continuous at -1. It's a removable discontinuity. It has a separate value and stuff. So whenever you have this kind of jump, that's a removable discontinuity because the limit exists going to the same value point from both sides, but at that value, it's a different number altogether. So let's look what happens to these things. So what are our numbers in particular? What values are we looking at to examine? We're going to look at 1 because we have a jump discontinuity. We're going to look at 2 and 4 because they have the removable discontinuity. What happens at 3 or at 0, for that matter of fact? Are they continuous? Yes. So looking at that, we know our domain is from 0 to 4. So now we look at everything inside there. The endpoints we look at separately, and the interior points, everything between 0 and 4, we look at those judiciously as well. So let's look at the first one. I should have had the graph up there. So what happens? What the points of discontinuity? Numbers where we have a break. So what numbers give us a break? Where is there some sort of discontinuity? 1, 2, and 4. Those are the ones we're going to look at first, because we know there's issues at those points. No, that's don't worry about that. That's algebra. Thank you, though. At 1, 2, and 4. The graph here again. That's what the graph looks like. So what do we know at 1? Again, 1, 2, and 1 and 2 are called interior points. Why are they called interior points? Because they're inside the domain, right? 4 is not interior points because it's one of the boundary points. So we know, let's look at x equals 1. What happens there? It's a jump discontinuity. Continuity because the limits from the right and left exist but are not equal. That's by definition what a jump discontinuity is. The limit as x approaches 1 from the left and the limit as x approaches 1 from the right. What are their values? So this one and this one is 1. This one means from the left, it's going to 0, and this is from the right, it goes to 1. They're not equal. There we have a jump discontinuity. It's a discontinuity, yes, but we put a name to it. So f of x is not continuous at x equals 1. At x equals 2. What do we know there? Do the limits approach the same value? Yeah. So here we have the limit as x approaches 2 from the left and the limit as x approaches 2 from the right. They both equal what? 1. But what's the problem? At 2, it equals what? 2. So if you look here, we're building up a definition of continuity. This is so far our best look at continuity. To be continuous, what has to happen? The limits from both sides have to be the same, and the value of the function at that limit point has to be the same. So if this was 1, then it'd be continuous. Right now it's not. Because of this, that makes it a removable discontinuity. And this is going to play a part in our lecture later on. We can make it continuous by redefining the domain or the values we're going to. Right? The next one, let's look at what happens at 4. There's a break there. We got to put the graph here. So at x equals 4. What happens at x equals 4? Does it have a left-handed limit? Does it have a right-hand limit? Does it need a right-hand limit? Why not? Because it's a closed interval. Because what's important, we have to remember this, that a function continuity, a function is continuous on its domain. That's going to play a pretty big important step for us in a little bit. So the limit as x approaches 4 from the left, what does it equal? 1. Because it's an endpoint, we can also say then that the limit as x approaches 4 from the right also equals 1 because it's at the bound of its limit. But what's the problem at it? When 4 equals 1/2. Again, because of that, it's a removable discontinuity. Looking at the graph, let's look at numbers where there are no breaks. And that only happens where? Why 0? Right. Because it's neither a jump discontinuity or a removal discontinuity at those 2 points. Because the limit as x approaches 0 from the left, the limit as x approaches 0 from the right, and the value at 0. They all equal 1. The limit as x approaches 3 from the left, the limit as x approaches 3 from the right, and at 3 our picture, they all equal 2. One, 0, 3, 1, 2, 4, right? So, according to our question that's asking us, which numbers of the function appear not to be continuous? We did that. That's 1, 2, and 4. Why? We just discussed that. What about other numbers in the domain? Are those all the numbers in the domain? Those are all the integers in the domain. What about at 1.5? At all other interior points, other than the integers, the functions are continuous in those subdomains. Because at this point, they both approach the same value. At this point, they both. So at all other interior points, it exists. We have to, because it has to be at every x. For it to be continuous, it has to be at every x inside the domain. So let's look at the formal definition. Let C be a real number. Oops. That is either an interior point or endpoint of an interval. Has to be a closed interval. Why does it have to be a closed interval? It goes with semantics. Can C be an endpoint if it's not included? No. The only way it can be an endpoint is if it's included. So here we're about a closed domain. Of the of an interval in the domain of our function. The function f of x is continuous at C if this exists. The limit as x approaches C of the function equals f of C. So that's the first check. Remember, whenever you ask to do find a limit, what do? Plug it in there, see if it works. So first off, it has to be a number in the answer. It has to be an answer. So this is the first thing we check. The second thing we check is the limit of the function as x approaches C from the left also has to equal f of C. And the limit of f of x as x approaches C from the right also has to exist, and they all have to be the same value. So That is what defines continuity. Actually, we could even go one further and say the function f of x is continuous at c if and only if these conditions exist. Because if any one of them do not exist, it's not continuous. There's some sort of issue with it. We say that a function is continuous on a closed interval if three things exist. It's right continuous, left continuous, and continuous. Why are those true statements? What does right continuous mean? Remember, in order for it to be right continuous, that means from the right-hand side, all of the values of x approaching c have to exist. All of those values to the right of c have to exist. The same thing, left continuous. If it's left continuous, all the x values approaching c from the left, all of those have to be defined. And together they have to approach the same value. The value at that point itself in between of all these. So this works for closed interval, open intervals, or partly open intervals. Whenever you deal with infinity, then it's a different issue. It doesn't have to be a closed interval at that point. Why? Because we can never get to infinity. Can you ever take a limit of infinity? We will talk about that in class in a later date. But can you take a limit as x goes to infinity? I have one yes, one no, and a couple of I don't knows, and there's another yes. Think about it. What as x goes to infinity of the function 1 over x. As x goes to infinity of the function 1 over x. What does the function 1 over x look like? Remember from algebra? The rational function? So, right. It's exactly right. It's when x gets closer to 0. Can x become 0? No. Can x have 0, be 0 in the function? What's the domain of this equation? Okay. Can we use 0? No. So yes, our domain is going to be negative infinity to 0. We can't use 0. And from 0 to positive infinity. That means we have to have two separate graphs. The larger x becomes, what happens to this number? As x goes to infinity, what happens to this number? It gets closer to 0. What happens as x gets smaller? Well, when x is 1, we know which one. When x is 1/2, what is it? When x is 1/10, what is it? Remember, let's see algebraically why. If we have a fraction over a fraction, what do? Take the top fraction and leave it alone. Flip the bottom one. So it's always going to be the reciprocal of the denominator. So if the bottom is 1 over 100, it becomes 100. So the smaller it becomes, smaller x is, the bigger the number becomes. So here's what the graph looks like. And then if it's negative, then it's on this side. That's the graph of the rational function. Is it a continuous function? Yes, it is. I know it's going through your head. How can you just said? You said by definition is if you could draw it undisturbed. But the optimal phrase was in its domain. What is its domain? From negative infinity all the way to zero. Did I pick my pen up? No. Now I go to the other half. I pick my pen up? No. So within its domain, it is a continuous function because x can never equal zero. Trick question. Let's look at an example. Example 2. The function f of x equals square root of 4 minus x squared. On the domain -2, 2. Prove continuity. Prove the function is continuous. Show f of x is continuous. What do you have to prove? What do you have to show to be continuous? What are the only critical points you have to examine? What does the graph look like? What? No. I see what you're thinking because you're thinking, okay, the rational function looks like this, but look inside there. What is that? It's the equation of a circle centered at 0, 0 with radius what? Because it's a squared plus b squared equals c squared. Did I show you how that defines circles? Or in algebra? What formula is this? Pythagorean. Pythagorean theorem defines what? Right triangles. How do we go from triangles to circles? Yes, but what exactly is a circle? We'll come back to this in a second. What exactly is a circle? Don't give me that. I can't put that in words. Or don't give me that. I get a lot of those people who just you tell people who just been to weddings. It's something that can never be beginning. There is no beginning. There is no end. Like the ring, the way. No, a circle, an infinite number of points that are all equidistant from a center point. And you're right. It's because it has to do a lot with the radius. So it's an infinite number of points that are all equidistant. Equidistant. That's the distance formula. What is the distance formula? This is where it gets cool. The distance formula is that. Or actually, we're first used to seeing as A and B. Pythagorean theorem again, isn't it? So how can the distance formula, which is the length between 2 points, the Pythagorean theorem, which is a triangle, all relate to circles? Any point we have from a central point, that's the distance. This distance, because of this formula, we create a right triangle. The same thing over here. Has the same distance, it creates a right triangle. Over here, same thing. And I keep on going. If I have enough of these dots, okay, this is awful, but you get the idea. Each one of these dots all have a distance from the center. And the more dots I have at the end of this distance, which we call a radius now, we now have a circle. So this distance is the radius. It's x plus h squared, y minus k squared, which gives us the equation of a circle. Because you don't have to stay at the origin anymore. This is the center, which is hk. If it's 0, 0, if it's the origin, then we have x squared plus y squared. But if it's anything else, any other point, then that's hk. Pretty interesting? Yes. Which has always fascinated me is how we go from a distance formula, which defines a right triangle, which now defines a circle. Kind of like in metric system. What is, when you hear people say 1cc, what are they talking about? Oh, that's okay. Thank you, sir. All right. What you ever see these doctor shows when they have injections? I mean, 3 cc's of this. That's a liquid, right? But what does cc stand for? This is remember, it's a liquid. It stands for cubic centimeter. Cubic is not too much of a liquid, is it? That's how much liquid fits in that 1 centimeter cube. That's always blown my mind. How we can talk about a liquid measurement which has no shape as a perfectly shaped cube. So anyway, that's just I don't I know what you think about it. It's true. How do they do that? How could they measure? here's here's some liquid. Measure 1 cubic centimeter out of that. You couldn't freeze it and do that because the ice has too many air pockets in it. So yeah, that's always boggled my mind. Simple things. Anyway, let's back to this. So, which brings us to the continuity test. a function is continuous if, or at C, if and only if the following exist. F of C exists. That's, you plug in the value C in there, it's actual number. The limit as x approaches C of the function equals L. It exists. And A equals B. Both of those values have to be equal. The limit at our function as x approaches C has to equal f of C. Is this all? No, because how do you define the limit? In order for the limit to exist, what has to be true? In order for the limit to exist, L at C, what has to be true? In order for the limit as x approaches C to exist, two things must exist. We have to be able to go from the left, and we have to be able to go from the right. Has to be both sides. So you see, we just expanded the definition of continuity, the proof of continuity, into the function has to exist. It has to be exist from the left side, from the right side, and they all have to be the same. Prove that that's continuous. Show is continuous on all real numbers. First off, what's the graph look like of the absolute value? You don't know. How many of y'all remember the library of functions? I don't mind going over those with y'all one day. Who wants to go over a review on that? Because there are 12 different ones that we use. Okay, I'll bring you some forms, some sheets tomorrow, and we'll go over that. Yes, so the absolute value is of E. Because remember, when you drop the absolute value, it becomes the negative x, and it becomes a positive x. So you have a negative slope and a positive slope. At 0, you have nothing. So at all of the interior points, we know that they exist because they're linear equations on both sides. This is for x is less than 0, and this is for x greater than 0. So really, for the interior points in the domain, we really don't have to worry too much about it. What we look at is what happens specifically at the critical points. In other words, what happens mostly when x approaches 0? From the left what happens when x approaches 0 from the right, and then what happens when x becomes 0. So what's the limit of this function as x approaches 0 from the left? Yeah, it's always going down, 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 down. So we'll go to 0. From the right-hand side, as we're approaching 0, it's going down, 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 down. It's approaching 0. What is it at 0? At 0, it's 0. So all three of those, there you just proved your continuity of the function. What's interesting is we see it's continuous on the entire domain of the function. But we're also going to see later on that the absolute value function has other limitations when it comes to differential calculus. We may not be able to take it. How about the greatest integer function? How about that one? We could look at this on the entire. Wait, does everybody know what this means? It means for sale. No, it's realtor symbol. It means all real numbers from negative infinity to positive infinity, which is what kind of why they use it. Is there's no limitations. We service everybody from everywhere, so that's negative infinity to positive infinity. What's the graph look like? What's the name for this function? It's called the greatest integer function. The name gives it away. We only use integers. Even though the domain is all real numbers, the answer is only integers. What helped me memorize this formula, which I call the round down function. For any x positive to the right of 0, truncate the decimals. So if x is equal to 0.3, the answer is 0. If x is 0.9, the answer is 0. If x equals 1.0, the answer is 1. If x is 1.3, the answer is 1. So on the right-hand side, truncate all the decimals. So at 0, it's 0. At 1.0, it jumps up. So all those. All these exist. At 2, it jumps to 2. And so on and so forth. It's also called the stair-step function. You keep the same pattern going down into the negatives. But that's the algebra approach. How do we prove it using calculus that is it continuous? What's the domain? Yeah, negative infinity to positive infinity. What's the range? Integers. Actually, it'd be n. Only integers. Because you notice the y values don't exist at decimal points, which is now why we can prove it's not continuous. The limit as x approaches 1 from the left is equal to what? 0. As we approach 1 to the left, it's always 0. The limit as we approach 1 from the right is 1. So we have an infinite number of jump discontinuities with the stair-step function. What do you think? If you understand the function, if you can visualize in your head, it makes it much easier to understand these things. Because as I said, whenever you deal with mathematics, always draw the picture first, or a picture first. If you have a rough sketch of the graph, then life makes life much easier for you. That's why we have to know the library of functions. Which is say ways functions can fail to be continuous. Is that a continuous function? No, obviously not. Why? Because at 0, the proof of which we have to go through all of these So as x approaches 0 from the left, what do we get? Oh, this should be 1. That equals 1. As it approaches 0 from the right, equals 1. At 0, it's undefined. Because it doesn't exist at that point, then we have a big a problem, since it doesn't contain the value x equals 0. What if we had a removable discontinuity? Because we're going to see how we can fix those later on. Is it continuous at 0? Can we make it continuous at 0? How? How would we do that? There's always we can do this. Because again, the limit as x approaches 0 from the left equals 1. The limit as x approaches 0 from the right equals 1. The limit, the function at 0 is 2. It's a removable discontinuity. We can make f of x continuous by redefining f of x as a piecewise defined function. Remember what a piecewise defined function was? Well, okay, we'll get that in a second. So we can fix that one. We can fix this type, removable discontinuity. Can we fix this type? What is this type called? We can't fix jump discontinuities because that would take rewriting the function itself, not just the domain. How about limits that go to infinity, which we call infinite discontinuities? We just talked about one of those. The rational function, 1 over x. What if we had 1 over x squared? Limits that go to infinity. So the limit of this one as x goes to 0 from the left. Again, we have to know what the graph looks like. Or really, we can plug in points to see what happens and we get closer to 0. This graph is the Atari symbol. Because it's squared, so it can't be negative. So it's the same thing on 1 over x on both sides. So as x goes to 0 from the left, what happens? Where does the answer go? It goes to infinity. Likewise, if we take the limit from the right, it's going to be infinity also, but we can't fix them. There's no way we can fix one of these because it would take rewriting the entire function again or doing a transposition, a shift of one of them, which we can't do. If we did a shift of one of the side of the functions, then we'd have a jump discontinuity, which again, we know that jump discontinuities can't be fixed. By fixed, I meant can't be rewritten so it becomes a continuous function. So if they go to infinity, I use this one because they're going at least going to infinity together, but they can't touch. It's like the in physics when you learn about gravity and space. If two astronauts were lost if their spaceship broke and they got out in space in their spacesuits and they were 1 mile apart, would they ever meet each other again? Yes, because think of how vast space is. The nearest planets that have any gravitational acceleration towards them are light years away. So those everybody has the same gravity as planets do, depending on what makes it bigger is its mass. 6.62 times 10 to the negative 12 newtons. So together, I mean, they may be dead and their bodies decayed, but their bodies are slowly attracting each other. Would they ever meet? Well, again, no, because the limit of life, they'd be dead. And then eventually they'd collide, which is why galaxies collide. It's because they have everything has an attraction to it to another object. And we talk about oscillating functions. About with the sine x sine to 1/x. Remember that one? Why doesn't that limit exist? Why is it not continuous? Because it oscillates so violently, right? We don't know if it's a positive one or a negative one. It starts off pretty docile, but then it gets closer to zero. It becomes very, very, very violent. It just goes up and down. And you can't guess what it's going to be, positive or negative. So there's limit doesn't exist on either side. F of x equals 1/x is a continuous function. Why? That's not that. Let's go. Yes, but in a nutshell, in a more succinct reason why. Because what? Yeah, because it is continuous in its domain. Its domain is negative infinity to zero, zero to infinity. That's the reason. Do we ever use zero? No. We don't have to because it's not in our domain. How about why is that a continuous function? Hmm? Doesn't tell me why. You just described the function. Okay, we know the domain is negative infinity, positive infinity, but it's continuous because the limits exist equals 3, and the function exists at any point C and is 3. Because the limit as x approaches any C from the right or left equals that constant value. And any value you pick is always that constant value. And that's why it's the definition of continuity. How about the identity function? Why is that continuous? You could think about it. Because there are no points in there, no value C that would make it discontinuous. That would violate any rules of math. You can think of it. But now, again, what goes there? One, the limits exists. Equals f of c, which is c. F of x or f of c exists, and that's c. So any value you give me, if I have f of c, that equals c. So that's what said. So that's the reason why, because it satisfies the limit criteria and it satisfies the value existing criteria. All right, let's look at the properties. Remember last week, whenever we talk about the properties, I told you we're going to see these a lot. We have the sum, the difference, the product, the quotient, the constant multiple, all those. We'll see those in every topic we talk about. We're going to see examples for those. And then here we have some more. Theorem 8. The properties of continuous functions. If f and g are functions, that are continuous at x equals c, then 1. We have the sum rule that exists that says f of c plus g of c has to exist. F of c minus g of c exists. The constant multiple k times f of c. Since f of c exists, when you multiply by a constant, then it exists. The product rule says f of c times g of c also exists, because if f of c exists and g of c exists, then the product of them has to exist. The quotient rule says that f of c over g of c exists. And g of c cannot equal 0. The power rule says that f of c to a power exists. Clearly, because if f of c exists, then any number that exists to a power also exists. And then the root. If f of c is a number, then you can take the cube root of it or nth root of it. Let's see, is there an example? This is actually a rule that every polynomial is continuous. Think of it. Every polynomial is continuous. What is a polynomial? Because of the sum rule, each of these pieces are constant multiples times x. Well, x, you can plug in c in there, take a power of it. So those, by definition, the sum or difference of all bunch of continuous pieces is continuous. So we know here that as x approaches c of any polynomial is simply that polynomial at the power c. It also works if we have the quotient. As long as q of c does not equal 0. So again, you see why polynomial functions exist and are continuous. The only way they wouldn't be continuous is if our exponents were negative. Ooh, what does that mean? Why would negative exponents throw a wrench in our picture here? How do you mean? It'd be a root if it was a radical or rational, I mean. Because I see what you're saying. X to the power 1/3 is the cube root of x. But if our exponent was -2, now we have a rational expression. Automatically, now it's no longer continuous, because if our polynomial was defined over the entire domain, negative infinity, positive infinity, except one part of it is negative, then that ruins it for the whole polynomial. Because now it can't be 0 on the bottom. It's no longer part of that domain that our original polynomial had. So that's what we have to be very careful about. And how about exponential functions? What about those two? What does an exponential function look like? Exponential function look like? Oop. An exponential function is where the variable is the exponent. What does that graph look like? Actually, there are two of them, depending on what our base is. Remember this? Very good. It just did a samurai ninja thingy. So because A has to be positive. Because if A is negative, remember, X changes. If X is even, it's positive. If X is negative, it's odd. It's negative. So in other words, we would have an alternating graph if A was negative. So A has to be positive. Then we have two conditions. If A is between 0 and 1, and if A is greater than 1. This is our base. If a is between 0 and 1, then it's a decreasing function. And it always crosses through 1. Why does it always cross through 1? Very good. Perfect. Because when x is equal to 0, anything that's above 0 is 1. Very good. That's why we're sure that it's always going to cross through 1. If a is positive, greater than 1, then we have that function. So are they continuous? Yes. Because there are no discontinuities in there. And and the domain is all real numbers. Negative infinity, positive infinity. So the domain is all real numbers and it's a continuous function. How about logarithmic equations now? How many of y'all remember things from logarithms? Well, there are 3 different types. Depending on what the base is. This is the base. If the base is 10, then it's a natural log, a common log, I mean, because we have our numeric system is base 10. If it's, and that's what this deals with. So it has no number down there. It's automatically a 10 that's down there. And then if it's base E, then it's a natural log. And it's an ln function, which is what we do mostly for anything to deal with biological items. Anything that lives, dies, it grows and decays, we use the ln function. So what does this graph look like? Instead of crossing the y-axis at 1, it crosses the x-axis at 1. Logarithms and exponential functions are inverses of each other. They're opposites of each other. Ooh, I should talk about that. Oh well. Is it a continuous function? Yes. Why? Because what's the domain of a logarithmic function? Anything greater than 0. You cannot take a log of a negative number, or you never take a 0. So it has to be greater than 0. And that's why that looks like that. So far, so good. So if it's a polynomial, polynomial functions are continuous functions automatically. What about inverse functions? Inverse functions. We kind of just talked about those when we did the the exponential and logarithmic functions, because they're inverses of each other. We know a function is an inverse by this little symbol there, the -1. How do we find inverse functions? Switch x and y, solve for y. That finds the inverse function. So because we switch x and y, so if f of x is continuous, then its inverse is also continuous. Because it goes with the algebraic definition. If a function is continuous, I mean, if a function exists, then its inverse is also a function. So this takes it one step further. If a function is continuous, then its inverse is also continuous. Case in point. Remember, if you graph inverse functions, they're simply symmetric about the line y equals x. This is f of x, then this is inverse of x. What about composite functions? What can we say about continuity there? First off, what are composite functions? Functions within functions. In algebra, you always talk about the Fogg and Goff method. Remember those?
Mhm.
Instead of Fogg, it really means f of g. It means the function of f with respect to the function of g. So, how does this relate to continuity? If here we have f. If f is continuous with respect to x, and then g of x is now it's continuous with respect to gf of x, that means the whole function is a continuous function. So if it's continuous at c, then we have f of c. And if g is continuous, then we have gf of c. It kind of has to do with the same thing as the polynomial. If each part of a polynomial, of the internal parts of a polynomial, if each one of those are continuous, then the entire polynomial is continuous. Same with a composite function. If g of x is continuous, then being an input, a continuous input into another function that's also continuous, the answer is going to be continuous. So if the function is continuous at c, then its composition is function is continuous. Let's look at some examples on this one. And then I'm going to ask you, why is continuity important? But not just yet. Show that these are continuous. On their natural domain. That's important. I almost forgot about that. Whenever you talk about continuity, you have to just specifically define its domain, what domain you're looking at. Remember when we did that? We haven't finished that one yet. The square root of 4 minus x squared. I gave you the domain. Why is it negative 2 to 2? Okay, we'll go back in a second. Let's do this one first. Show that this is continuous. Is this a composite function? You have an internal function here, right? Then you have an outer function. Then that's what you have this. The inside goes in here, you have a composite function. So it is a composite function, compound function. Is it continuous? Well, you have to look at two parts. Is the internal function continuous on the domain? Yeah. There's nothing here that says it doesn't exist. I could plug in negative for x. I could plug in 0 for x. I could put positive for x. Now, what about this one? Is this a continuous function? Remember, it says on its natural domain. So this domain is all real numbers. This domain is what? Greater than 0. So, is this one continuous on this domain? So since this one is continuous on that domain, then this one is, that means the whole function is continuous. So the composition of two continuous functions is a continuous function. That's what we just showed you. The composition of two continuous functions is a continuous function. Y equals x to the power 2/3, 1 plus x to the 4th. Is this a composition of functions? Yes. And there are many ways you can write this one. You can say f of x is 1 over x. G of x is 1 plus x to the 4th, x 2/3. If I plug this inside there, I get this reciprocated. So are they continuous functions? Is the numerator continuous on the domain of all real numbers? Yeah. I could put negatives in there because a cube root of a negative number is a negative number. I could put 0 in there. I could put positives in there. Now the question is, does the bottom one allow me to be continuous on all real numbers? Can this ever be 0? No, because it's an always positive function. 1 plus positive number is never going to be 0. The only way it could be 0 is if they're negative of each other. So this one's always positive. So it's a continuous function on all real numbers. Can never be 0. This one's continuous on all real numbers. Can it be 0? Yes, but it doesn't matter if it's on top. So that means the entire function is continuous on all real numbers. Is this one continuous on all real numbers? How about the top? It is continuous on all real numbers. Yes. Is the bottom one continuous on all real numbers? Yes. But now we have a rational, or is the entire rational function real and all real numbers? In other words, what's the only thing we don't want? 0 on the bottom. Can that ever equal 0? Those are ones I can't use. It's continuous on all numbers other than x equals plus or minus radical 2, because that makes the bottom equal 0. On all x except plus or minus radical 2. Why is that important? Because now we could redefine our domain as being that's my new that's my new domain. The trig function. Next example. Is the numerator a continuous function? It's a product, 2 parts. Are they both continuous functions? Is x a continuous function?
Yeah.
Is sine a continuous function? It's a sine wave. It goes on forever and ever. So that's a continuous function, the product of them. How about x squared plus 2? Is that a continuous function by itself? Yeah, it's a quadratic equation shifted up 2 spaces. Together, are they a continuous function? Are there any places that can't exist? Can the bottom ever be 0? No, it's a positive function. X squared plus 2 can never be negative or 0. So it's always a continuous function. So this one on all real numbers. Ooh, these a little bit more thinking here. The limit as x approaches pi over 2 of cosine 2x plus sine 3 pi over 2 plus x. This one, the theorem that we're using is this. If the limit as x approaches c of our function f of x, if that equals some value b, then the limit as x approaches c of g of f of x equals g of b. This will relate to what we're doing here. Notice the G is the same. The only thing we did, what's missing here, let me show you what they did here. That's the way they got G of B. So if you have a composite function, that means here the cosine stays out in front. Now I'm taking the limit of everything inside there. So this is the outer function. This is the I want to say, but it's like the constant multiple. It goes out in front. I'm now taking the limit of the inside, which is what we just did here. So what happens here? When x becomes pi over 2, what does this one become? Pi. Because we have, well, let me plug everything there. Pi over 2. Plus, now we have sine 3 pi over 2 plus pi over 2 equals cosine. The 2's cancel, so it's pi sine 3 pi over 2 plus pi over 2 is 4 pi over 2. What is sine of, well, 4 pi over 2 is actually 2 pi. What is sine of 2 pi? 0. So cosine at pi is what? Remember your trig numbers? Yeah. Pi is over here. This is pi, this is pi, and this is 2 pi. So the answer is -1. You're right, it's a 1, but it's negative sign because it's on the left-hand side. So we'll do the same thing in the next one. This is inverse. See if you remember what your inverse function is. The limit as x approaches 1 of sine inverse of 1 minus x, 1 minus x squared. Remember, always do the algebra before you do anything calculus-y. What can we do inside the parentheses? What's that? You can factor it out, right? X approaches 1 of the inverse of sine. So it's 1 minus x on top, 1 minus x, 1 plus x on the bottom. So the 1 minus x's cancel. So now we're just dealing with 1 over 1 plus x. And the inverse of the limit as x approaches 1 of 1 over 1 plus x is 1 plus 1 over 2. Because x is 1. So what's the inverse sine of 1/2? Where does sine equal 1/2? It's not, we know it's not pi over 4, but that's square root 2 over 2. So it's either pi over 3 or pi over 6. 50-50 shot. You're thinking of cosine. Cosine pi over 3 is half. One more. But remember, inverse trig functions. This is not the angle. It's what this is asking is the inverse of sine of this is what is the angle of sine that gives you this? You have to work backwards. So this is the answer. You have to tell me what x gives me the answer for the inverse. And C, we have the limit as x approaches 0 of square root of x plus 1 e to the tangent x. We have a product rule here. So we have two parts. We have the limit as x approaches 0 of the square root of x plus 1 times e to the limit as x approaches 0 of tangent x. So what's the first one? Limit of the square root of x plus 1 as x goes to 0. So that becomes 0 plus 1. It becomes 1. And this one, what is the limit? When x goes to 0, what's tangent of 0? Remember, it's sine 0 over cosine 0. What is sine of 0? Cosine of 0. So that's 0. E of 0 is? Let's see what else we're going to do today, though. Well, next, we have a couple more things next time we'll talk about it tomorrow of the mean value, the intermediate value theorem, and we're going to talk about how to transform a discontinuous function into make it continuous. Okay, I'm sorry I kept you all a little bit long today.